recall we are looking at the integral of sine x to the nth power and times the cosine x to the nth power dx. In this case, m is 2k plus 1. Once again, k is an integer, and we're going to work out the sine so that the idea is to factor sine x to the n power so that to have let's see, so we have the sine x by itself, and therefore we'll end up having sine x dx. So actually I should have added the x here, but this is what we are looking for. We are looking to end up with a single power of sine x. Okay, so k is an integer, and let's see how this works. The integral, we start with and we'll factor it. We'll first write it as sine x to the 2k plus 1 cosine x to the nth power dx. And we're going to do what we did before. We're going to break it down into the sine x to the 2k times sine x times cosine x to the nth power dx. And we take this and that will make it our differential. And we're going to write sine x to the 2k is sine squared raised to the kth power, and then cosine x to the n power, and finally we have the sine x dx, which is the idea behind it. And this is what you need to really understand rather than remember one formula or another. Because what you're going to do in general, we're going to let now, we want, because we have sine x dx, we want everything else in terms of cosine. Okay? So you have the differential, and everything else need to be in terms of the cosine, and to do so, we could just replace the sine squared with 1 minus cosine squared. And now we are very comfortable because everything, the integrand without the differential, sine x dx, is all in terms of cosine. So now come the substitution. Let u equal cosine x, and therefore du equals negative sine x dx. So the only thing is, instead of having 1 minus u squared because of the negative, well, I do it slowly. Instead of, well, we start with 1 minus u squared to the power of k. I'll keep it like that, actually. And then cosine, I'm sorry, this is u to the power of n. I was struck for a second. Du times negative du, sorry. Ooh. Or I'm going to end up writing negative 1 minus u squared to the k power u du. So what is the formula for the formula lovers? If you have this kind of arrangement, then the result will be negative integral. I don't know why I'm writing it again, but so let's box this one. Thank you. U to the n. I'm sorry, I omitted that. I had a little accident right here. And we need to remember that where u is the cosine. Here comes an example. And let's see, this will be example 2 in this case. Okay, what we need to evaluate, this time I'll give you a real product. Let's evaluate the integral sine theta to the 5th power, and we leave the cosine at cosine squared in this case. Again, what I'll do, I'll write here solving without the formula. So instead of jumping right here and replacing k and n, I just want to go back to the basic idea, and here's the integral. So we start with sine x or theta to the 5th power cosine squared of theta d theta, and because we have the 5th power, we're going to break it down into sine to the 4th times sine, and then cosine squared of theta d theta. Okay, again, this is the goal, to combine these two together. So sine to the 4th is sine squared squared, like so. And because I have sine theta d theta, I want everything in terms of the cosine, so I'll have 1 minus cosine squared cosine squared sine theta d theta. And now I'm ready to do the substitution, the u substitution. Why is that? Because everything, the integrand is all expressed in terms of the cosine, while the differential is sine theta d theta. So we let u equal cosine theta, and therefore du equals negative sine theta d theta. Notice that I'm not even looking at this formula. I'm using this just as a generic example. And now after the substitution, I'm looking right here. It's the integral of 1 minus u squared u squared negative du. Okay. The rest is algebra, and then simple integration of a polynomial. So we'll stick the negative up front so we won't forget it, and then we clear this the square, so we have 1 minus 2u squared plus u to the 4th, all of it multiplied by u squared du, and we get to negative u squared minus 2u to the 4th plus u to the 6th du. And now we are ready to apply the antiderivative, or to integrate, and we get negative up front. And remember, u is what we need first to find the antiderivative. So we look at the u cubed over 3 minus 2u to the 5th over 5 plus u to the 7 over 7 plus c. And finally, bring back the cosine, and also clear the parentheses, so we end up having a negative 1/3 cosine cube plus 2/5 cosine to the fifth minus 1/7 cosine to the seventh plus c. This is quite a powerful tool. Think about that. Now, there is quite a way to go to check it. This will be, actually, to check it may be even harder than to integrate, because look what we are supposed to do. When you take the derivative of this result, you're supposed to get sine to the fifth cosine squared theta. You can do it, but it will take some trigonometric manipulations, the use of trigonometric identities until you obtain this result. Okay, so how we can check stuff like this? Well, one simple way to do is perhaps numerical value. Pick up a value for theta and plug it in. Those of you who are familiar with Wolfram alpha or any kind of integration technique, you may not obtain the same result, because we're dealing with trigonometric identities, and you can have different, the identities can be expressed in different ways, and that's one of the challenges that where you really need to do stuff manually if you want to compare. I mean, if all you need is to find a numerical value, then yeah, go for it. But if you need to do some analytic work, then sometimes computer algebra system won't help you, or Wolfram alpha or even the TI-89 will give you different results. But of course, we are not allowed to use this during the test. So.